Good day, everyone. I welcome you back to the 11th episode of Physics for SS2 course, and today we'll be dealing with waves, one very important topic in physics, which is very important in most aspects of physics. So I implore you to watch to the end of this video to gain as much as possible. Now, when we think about waves, we're talking about the process of transferring a disturbance in form of kinetic energy. So a wave is kind of like a disturbance that transfers from one point in a medium to another point without transferring any of the particles, but the only thing that is being transferred is the energy. That is called wave motion. But a wave itself is a disturbance which travels through a medium, transferring energy from one point to another without causing any permanent displacement of the medium. So it's just like when you imagine somebody passing through a place and pushing people aside, but when you push those people aside, they will still come back together. So that's how a wave is. It's like that person that is pushing people aside in a crowd is going in the opposite movement of the crowd, and when he passes through the crowd will still converge. So that is how a wave is. It doesn't change. It doesn't permanently displace the particles, but it gives them energy. So that energy is converted to the kinetic motion of the people when they move aside. So that is how I want you to understand a wave. It's kind of like the most practical example. Now let's talk about one example of wave, and this is basically a mechanical wave. So in this case, we have a mechanical wave, and this wave involves a pulse that is moving down a rope. Now a mechanical wave is a wave that needs um material medium. So it is a wave of any material object. It's called a mechanical wave. And now these mechanical waves, they have their material objects. They are pushed aside by these waves. Now when you start up a wave, when you shake a string up and down, you will set up a wave in the string, as you can see in the first picture. So that wave goes up and it moves from your hand towards the point of attachment of that string, which is the wall. So when it's, you can see that in the three stages, the wave is moving and it's traveling towards the right. That is called wave motion. Now in this case, let's look at one apparatus. It's called a ripple tank, and it is used to produce continuous water ripples or pulses in the form of water waves. So, and this is done by disturbing the water surface continuously. So basically, the ripple tank consists of a pool of water in shallow tray with a transparent base, which enables us to project the images of the waves on a screen placed below it. And the tray is leveled such that it is perfectly horizontal. A dipper in the form of a horizontal metal strip or a small sphere touches the water, and a vibrator in the form of a small electric motor to vibrate the dipper, and a lamp fixed right above the water surface to illuminate it. So this is the diagram of a ripple tank, and you can see this is a motor. That motor vibrates the water surface, and because of that, those vibrations, there are disturbance, and those disturbance create waves in the water, and these waves can be viewed through a stroboscope. Now this stroboscope can be set up in such a way that the continuous wave can be made to appear stationary so that it can be studied in more detail. So this is the apparatus that is used to study waves. Another concept which I want to explain in this video is the concept of wavefronts. So for plane waves and spherical waves, they both have their wavefronts. For example, you can see the circular wavefronts. Basically, a wavefront is basically a line or surface in the path of an advancing wave on which all the particles are in the same phase or state of vibration. So in this first example, you can see that the wavefronts, they are concentric circles, right? Now each of these circles represents a wavefront because all the particles are in the same state of vibration. For example, they are in the same distance from the center of the vibration. So that's an example of properties of circles in the properties of particles in the same wavefront. And in a plane wavefront, they are at the same um, distance from the center also. They are on the straight line. So this is a wavefront. It's characterized by the state of vibration. In science, we've been able to come up with a way of representing waves, and this is called the graphical representation. We have graphical representation for transverse and longitudinal waves. For transverse wave, a transverse wave is a wave that in which the waves travel perpendicular to the direction of the vibration producing the waves. So in this case, the wave is traveling perpendicular to the direction of the particles of the medium, whereas in longitudinal wave, the wave is traveling in a direction parallel to the particles of the medium. So you know that the particles of the medium are actually vibrating. They are being pushed aside by the energy that is given to them by the wave. So when they are pushed aside in the direction of the wave motion, it's called transverse wave. It's called longitudinal wave. But when they are pushed aside in a direction that is perpendicular in the 3D plane to the wave motion, it's called transverse waves. Now in this case, this is a wave representation. This is how we represent a wave. Now you have the positive displacement. The maximum positive displacement is the crest, or rather, let's call it the highest point on the wave, on a particular wave section. Then the lowest point on the particular wave section is called the trough. Then we also have the amplitude, which is the highest total displacement from the mean or equilibrium position. So this is the progression of a wave with time, and you can see this wave, it looks regular, but not all the case, because when you listen to the audio, when you look at the audio track of some music, maybe if you are into sound production, you'll see that most of it looks like waves, but the waves, they are not always as regular as this. They are combination of different frequencies and different waves. So in real life, our waves are much complex than this, but this is just a sample of just one single um, type of wave out of a group of waves. On the other hand, this is the representation of the progress of a longitudinal wave. Now you can see that this longitudinal wave, it consists of the particles. The lines are basically in the plane. So these are consisting of parallel lines that are in the same plane of vibration. So that's because they are longitudinal, and so the vibration of the particles of the medium are parallel to the progression of the wave. So you can see that there are different distinct sections. There are the section in this in the B part of this diagram. You can see that sometimes the lines are close together, sometimes the lines are sparse, and sometimes the lines are dense. Now when the lines are close, it's called a compression, and when the lines are sparse or have a lot of space between them, it's called a refraction. Now this, when you represent this wave motion in the terms of in a graphical method, you will have a graph like C. So in this C, when you look at it in the how it looks like, it looks in the same way as this. It also looks like a wave. So but in the graph in the pictorial method, it looks like a group of compressions and refractions placed side by side alternatively. That is basically how a longitudinal wave looks. Now let's talk about the different terminologies that are associated with waves. So just bring back that image of a wave, a transverse wave, which I talked about earlier. Now when we talk about such waves, we have different things we talk about in the motion of the wave. Now the dots on the graph represent the position of the particles at that instant. So when you have dots on the wave, it is basically the position of the particles at that instant, and the arrows indicate the progress of motion of this particle. So the arrow from left to right indicates the time that, or the rather, you can just call it the distance moved. That is the x distance. While the y on the y-axis, you have the y distance. So you have the x horizontal distance on the horizontal axis, then you have the y or vertical distance on the vertical axis. So basically, particles which are at the same vertical distance from their position of rest are and are moving in the same direction as shown on the graph are said to be in the same phase. So that is what we know about phase. Then we also have a cycle. A cycle is a complete to and fro movement of oscillation of a vibrating particle. So when a wave moves in a whole circle, so when a wave moves, like let's call it 2 pi, a distance of 2 pi, an angular distance of 2 pi, it is called a circle. So that is what consists of a wavelength. So some moments ago I mentioned that the amplitude is the maximum displacement of a particle from its rest position, which is also known as the equilibrium position. Now let's talk about the wavelength. The wavelength is the distance between two successive crests or successive troughs, or two successive points in phase on a wave. It is measured in meters. Then let's talk about frequency. When we're talking about simple harmonic motion in a previous episode, I talked about frequency being the number of complete oscillations or vibrations in 1 second. So that is the definition of frequency. And remember that we also talked about the fact that the frequency is the reciprocal of the period. Now the period itself is the time taken by the wave to make one complete oscillation. So that is the time divided by the number of oscillations. So basically these are the major terms and terminologies we use in waves. Then we also have the wave speed. The wave speed is the distance which the wave travels in 1 second. and it is measured in meter per second. Now, with all these terminologies in our pocket, we can be able to understand completely and analyze the nature of waves. Now, here's a problem that helps us to understand wave more. And this question says the frequency of a vibrating source is 450 Hz, and the velocity of the sound it produces in air is 330 meters per second. Find how far the sound travels when the source completes 50 vibrations. So in this case, you are looking for the distance. You have the frequency as 450 Hz or 450 cycles per second. Therefore, the time for 50 oscillations is given by. So you have to, when you know that 450 cycles is performed in 1 second, so you can always know the time for 50 oscillations. That's 1 over 50 times 1 over 50 times 50. That's 1 over 9 seconds. That's the time taken for 50 oscillations. Next, we know that the velocity of sound in air so is 330 meters per second, and the distance traveled in time 1 over 9 seconds is given by Vt. So the distance of traveled by waves is the product of the velocity and the time. That's velocity is 330 meters per second times the time, which is 1 over 9 seconds. At the end of the day, we get 36.67 meters. That is the distance traveled by the wave. Now, waves, like any other phenomenon in nature, have their properties, and they have the things by which you can distinguish and understand them. And wave, they have major properties, which are reflection, refraction, interference, diffraction, and polarization. Now we'll start from talking about reflection. And when we talk about reflection, it's basically, if you understand it in the ordinary terms, reflection means for something to be changed or to be turned around. So when you see a reflection in a mirror, it's basically like you are seeing a turned version of you looking at yourself. So basically, the reflection is basically when a wave turns around or when it bends its direction. So in this diagram, you can see the direction of the wave. So when you have an incident wave front that is hitting a plane surface, now the direction of the incident wave front is changed, and the direction of the reflected wave front is different from the original direction. So and then when you draw a normal to the surface from that point of contact of the incident wave front, you will get a line which is called the normal to the plane, and then the angle between this line and the incident wave front is the angle of incidence, and then the angle between this line and the reflected wave front is the angle of reflection. Now these are the basic things you need to understand before you talk about reflection of waves. And in reflection of waves, there are some things we need to know. For example, the one basic law of reflection is that the incident angle and the reflected angle are equal. So when you are measuring them from the normal, they are equal. So reflection is one important part of waves that is applied practically in very diverse ways of life. Another phenomenon that occurs with wave, which we will discuss in this video, is refraction. Now, if you consider a plane wavefront traveling from a medium to another medium of different density, now when the wave travels from the first medium to the second medium, as wave is traveling at an angle to the plane boundary, it passes from the medium, and then normally it just suddenly changes its wavelength, speed, and direction. Now, the most obvious thing it changes is the direction, but the wavelength and speed, they are not very obvious, but they actually change. It changes its wavelength and speed, though the frequency still remains constant. Now, the refraction is a change in the speed and direction of the wave as they cross the boundary between two media of different densities. So the angle of incidence is the angle the direction of the incident wave front makes with the normal at the boundary surface. So we measure the incident wave front, and that's the group of waves that are hitting the surface or the medium. Then the angle of refraction is the angle of refraction is the direction of the refracted waves make with the normal to the plane boundary. So as you can see in this case, this is the incident wave front. When they hit the surface, they are at an angle to the normal, angle I. Then this is the plane reflecting surface. Then the first medium is colored light green and the second medium is colored yellow to differentiate it. Now when the wave has crossed the plane reflecting surface, you can see that the wave now deviates from its direction. So it's kind of like it's the direction of the refracted wave and its deviation. And this is called the deviation of light wave when passes through from one medium to another in the process known as refraction. Now, in short, once you see two mediums, once the second medium is less than the first medium, the ray is refracted away from the normal, and that normal is the line that is perpendicular to the plane reflecting surface. But whenever the second medium is denser than the first medium, the ray is refracted towards the normal. So those are just two shortcuts you can use to understand refraction. And refraction is very practical. It occurs when light moves from two mediums that are different. For example, when light moves from glass to water, and when light moves from air to glass. For example, even the television movies you watch, they get refracted from glass to air before they enter your eye. So this is one thing you should understand. It occurs in anywhere light moves from one medium to another. It always carries out the process of refraction. Before we continue studying the properties of waves, let's talk about progressive and standing waves. And yeah, we'll talk about the superposition of waves. Now, a wave which continues to spread out, transferring energy from the source of disturbance, is called a progressive wave, and its waveform is basically the typical wave that we showed in the previous some moments ago in this video. Now, on the other hand, a standing wave or stationary wave is set up when two equal progressive waves of equal amplitude and frequency and traveling in opposite direction are superposed or made to overlap or combine together. The resultant effect of the superposition of two waves of the same frequency depends on whether the wave arrive at a point in phase or not. So if they arrive in phase, they will be superposed in such a way that they will constructively interfere. But if they do not arrive in phase, they will destructively interfere. Now this is the general shape of a standing wave. For in this case, you can see that this standing wave is formed by the destructive interference of two waves of the same amplitude, frequency, but they are not a whole number in phase with each other. So that means they are not in phase with each other. Now the amplitude of the resultant wave is the algebraic sum of the amplitude of the two waves. So basically, the superposition of two waves of the same frequency and amplitude which are exactly out of phase results in the creation of a region of zero resultant disturbance. As you can see in this wave, when you add together the amplitude of each of these waves, the first wave and the second wave, you can see that they are both, it's just like adding a number and it's negative. So that will give you 0 at every point in this wave. That means at the end of the day, at every point in this wave, the resultant disturbance is 0. So this is called a stationary wave. It is obtained as a result of the combination or superposition of an incident wave and its reflected wave. So reflected wave is of the same frequency and amplitude as the incident wave, but both waves are exactly out of phase. Now because of this, they cancel each other, and the points marked N are the nodes of the stationary wave, and at this point the displacement is always 0, but the points marked A are called the antinodes. Now stationary waves are the waves that help us to listen and hear sounds from musical instruments, and stationary waves, they are also set up in many sound equipment, and they are very important in sound production and sound understanding how sound works. Now a node is a point on the stationary wave where there is no movement. So you can see the points marked N in this diagram. These are the nodes. So they are node displacement. The wave is directly at the equilibrium or resting position. But then when we talk about the antinodes are the points where the displacement is magnitude is maximum. So this is basically what a standing wave looks like. And standing waves also operate on the principle of interference, and it's called a destructive interference when the waves come in contact with each other when they are directly out of phase. If we decide to analyze the process of interference in more detail, you will see that when one source is when you have two waves moving towards the same position. In this case, these waves, they are moving towards the same direction now. Now these two waves, when one source is half wavelength closer to the point of combination than the other, that means if the path difference is half wavelength, then the wave no longer arrive in phase, but they are 180 degree out of phase. The reason for this is that one wavelength is 360 degree revolution, whereas half wavelength is 180 degrees. So that's why half wavelength is 180. Now the crest from one wave arrives simultaneously with the trough of the second wave, and the waves combine to cancel completely the effects of each other. So they are said to interfere destructively. This is another way you can understand interference Now, but you can see that in the first diagrams, the waves interfere constructively because this time around they are in phase. So you can see there are a whole number of wavelengths away from each other. But once they are not a whole number of wavelengths away from each other. That means if the path difference is not a whole number of wavelengths, then there will be some sort of destructive interference. And let's say interference is simply the effect produced when two waves of the same frequency, amplitude, and wavelength traveling in the same direction in a medium are superposed as they simultaneously pass through a given point. That is how it will occur. And superposition is basically when you have the waves going and merging into one together. Now, finally, we have come to the fourth property of waves, and this fourth property is known as diffraction. Now, we can simply define diffraction because when traveling waves pass through narrow openings to move around obstacles, they tend to spread out in different directions. So, this phenomenon is known as diffraction, and it occurs when the wavelength is longer than the length of one of the opening or the size of the obstacles. So when the wavelength is longer than the width of the opening, it's called that diffraction happens easily. It occurs even more easily in waves which have long wavelengths, like sound waves, but it doesn't occur more readily in light wave, which has a very short wavelength. Now, diffraction is the ability of waves to bend around obstacles in their path. We can demonstrate diffraction in ripple tank by having a region of space and opening, a small opening, and then you direct the waves towards that direction. And you see that when you have a narrow opening, the waves, when they hit that opening, they spread out and they become circular. Those they spread out in all directions, and diffraction occurs. So this diffraction is very, very important. It has a lot of important applications which we'll be talking about later in another aspect of this video. But diffraction occurs in basically all waves, and it is mostly pronounced in waves with long wavelengths. Now, folks, here we want to talk about the final property of waves, and this is polarization. Now, this final property is a very special property in that, apart from the fact that it has a lot of special application, but it also the property it has that it doesn't occur in all waves. It only occurs in transverse waves, and the reason for this I will tell you now. Now, this polarization is defined as the process whereby a wave occurs in only one plane, and that plane is known as the plane of polarization. So a wave is said to be plane polarized when its vibration occurs only in one plane. And now this polarization is a phenomenon whereby a wave whose vibrations are only in one plane is produced. So when you polarize a wave, you are producing a wave whose vibration occur in only one plane. Now, for us to understand what vibrations and plane means, look at this diagram. Now, in nature, waves are directed in different directions. You can see in this diagrams, you can see the arrows pointing in all directions. But whenever the waves pass through the polaroid, so this green rectangle with a smaller rectangle hole inside is representing a polaroid, and a polaroid is basically a substance that is used to make light vibrate in only one direction, such as tourmaline crystal, quartz, or another type of materials. They are all polaroids. Now, these polarizers, they are also known as polarizers. Now, these polarizers allow light to vibration of only a particular direction to pass through them. So in this case, when the light that is vibrating in all directions, when it enters that polaroid, the ones that are vibrating in a direction that is against the direction that the polarizer allows will be filtered out. So if the light that is not not vibrating in the required direction, it will be filtered out and it won't be able to pass through the polarizer or polaroid. So in this case, these polaroids, they will filter out the waves, and you can see that at the end of the day, you have a wave that is vibrating in only one particular direction. And then when you pass it through that same polaroid again, you are filtering it again and again and again, so you get a very, very pure wave which is vibrating in only one direction. So that polarized wave, they don't contain wave vibrating in any other directions. So this process is often used in making of sunglasses and all the rest. So all those sunscreen and sunshades, they don't let light of all directions come in, only in particular directions. Now you can see in the second diagram, if you turn the Polaroid in such a way that it is 90 degrees or perpendicular to its original orientation, you will see that no light will pass through it, because the direction which the wave allows is now perpendicular to the original direction which it was allowing. That means the new wave, the wave that was passing through, will not be able to pass through the direction because it doesn't align with the wave, with the direction of the wave. So that's how polarities are. They only let light pass through which is aligned with their allowed direction. So this polarization, you can see that this is the reason why it doesn't occur in any wave apart from transverse waves, because transverse waves can vibrate in all directions, whereby longitudinal waves are only vibrating in the same direction as the wave themselves. So longitudinal waves, they are always parallel, but when we talk about transverse waves, we can get waves directed in any plane, because when we talk about perpendicular plane in 3 dimensions can take any orientation. So that's why polarization occurs only in transverse waves. So of this video, this is a question I will give on the screen now. You can try it out, and as I used to say, you can send the answer to me on the WhatsApp number in the description of this video, or you can comment the answer. Thank you for watching, and don't worry, I will solve the question in a separate episode of this video.